Gas stoichiometry is just combining gas laws with stoichiometry to solve a problem. There are two main types. At STP, we're going to use molar volume. We learned this in the last chapter. When it's at STP, we don't need to use the gas law. We could use stoichiometry and then use 1 mole of X is equal to 22.4 liters of X. If it's not at STP, you need to figure out what gas law to use and then stoichiometry. Or you might have to do stoichiometry before you use the gas law. In this first problem from your packet, calcium carbonate decomposes to calcium oxide and carbon dioxide. So like any other problem, the first thing we do is we write a correct balance equation. Calcium is a metal, so this is an ionic compound. The charge of calcium is 2. The charge of carbonate, CO3, is 2, so it cancels out. So it becomes CaCO3. It decomposes into calcium oxide. Calcium has a charge of 2. Oxygen has a charge of 2, so it cancels out. Plus carbon dioxide, which is a nonmetal plus a nonmetal, so prefixes become subscript and subscripts become prefixes. So it's CO2. We have 1 calcium on each side, we have 1 carbon on each side, and there are 3 oxygens on both sides. So the equation is balanced. So it asks you to calculate the carbon dioxide from 152 grams of calcium carbonate. Since this is at STP, we don't need to use gas laws. I could use 1 mole of X is equal to 22.4 liters. So I'm going to start with what's given, which is 152 grams of calcium carbonate. Diagonal has to be the same, so this is grams of calcium carbonate. We know we have to go to moles because that is the only time we could go from one element compound to a different element or compound. So we're going to do molar mass to convert to moles. 1 mole of calcium carbonate is equal to 100.09 grams of calcium carbonate. We don't want the moles of calcium carbonate, so diagonals have to be the same. So moles of calcium carbonate to moles of CO2. The coefficient in front of CO2 is 1. The coefficient in front of calcium carbonate is 1. And since this is at STP, we could say 1 mole of CO2 is equal to 22.4 liters. Multiply the top, multiply the bottom, and divide. And you should get 34.0 grams of CO2. So if I do sig figs, conversion factors do not count, so there's 3 in the beginning. We could also solve this using gas laws. It just will take you longer. I still have to convert to the moles of CO2. So if I identify the variables, we have 1 P, and we want to use 1 ATM. We have 1 T, which is 273 kelvins. I'm going to already put it in kelvins because gas has to be always calculated in kelvins. And we're looking for the volume. Since we have 1 of each variables, we know we're going to use ideal gas law, PV equals nRT. We're going to plug in. So this is 1 ATM times volume. We need to find the moles. We know how to find the moles. Again, we're going to start with 152. We're going to convert it to mole, and we're going to find the moles of CO2. So if you notice, if I use the gas law, I need to pretty much do exactly what I did for molar volume, but extra work. So here, I would have to calculate this portion of the math that I did on top to find the moles of CO2 and plug in the gas constant and my gas temperature, which is 273. If I do my math, I would get exactly 34. If you notice, the top part was much faster and easier to do. So if it is at STP only, use molar volume. It will save you a lot of time. For number 3, methane gas has a volume of 2.8 liters at 25 and 1.65 ATM. This was mixed with oxygen having a different volume and a different temperature. We want to find the volume of CO2 when it's combusted. Since it's methane gas and oxygen, we know this is a combustion reaction. CH4 plus O2 yields CO2 plus H2O. So there's one carbon. I need 2 in front of water because I need 4 hydrogen. So now there's 2 oxygen plus 2 oxygen. So I need a 2 in front of O2. So I need to find a volume of CO2 at 2.8 atm and 125 degrees Celsius. But they give me information on methane and they give me information on oxygen. So I know this is a limiting problem. So if I look at the methane gas, so now I'm going to identify the variables. For methane, I have a volume of 2.80 liters. I have a temperature of 25 degrees Celsius. And I have a pressure of 1.65 atm. For oxygen, I have a volume of 35.0 liters. I have a temperature of 31 degrees Celsius, and I have a pressure of 1.25 atm. So for the volume of CO2, we don't know. We know the temperature is 125 degrees Celsius, and we know the pressure is 2.50 atm. Since each of these have 1V, 1P, 1T, I know my formula is going to be the ideal gas law. Since I have information on both reactants, I have to figure out if the methane is the limit or the oxygen is the limit. In order to do that, I need to calculate the moles using PV equals nRT. Because once I know the number of moles, I could calculate the moles of CO2 to figure out if CH4 is limiting it or O2 is limiting it. So I'm going to solve for the moles of CH4 using PV equals nRT. I'm going to solve for the moles of methane, plugging it in. The pressure is already in atm, so I'm just going to plug that in. The volume is already in liters, so I'm going to plug that in. This is equal to N of CH4. Gas constant 0.08206 atm liters, moles, Kelvin. Temperature needs to be converted to Kelvin, so plus 273. And solve for NCH4, which equals 0.189 moles. I'm going to repeat the procedure for O2. So O2, the pressure is 1.25 atm. The volume is 35.0 liters. This is equal to N of O2. Gas constant is still the same. The temperature needs to be converted to Kelvin, so we're going to add 273. Do the calculations, and NO2 be 1.75 moles of O2. So now I know the number of moles of CH4 and O2. I'm going to find the moles of CO2 to figure out which one is the limit. So starting with the moles of CH4, I'm going to do a mole ratio, moles of CH4. Moles of CH4, I'm going to go to moles of CO2. The coefficient in front of CO2 is 1. The coefficient in front of methane is 1. The moles of CO2 is the same as methane. I'm going to repeat the procedure for oxygen. So for oxygen, we're going to start with 1.75 moles of O2. I still have 1 mole of CO2, but I have 2 moles of oxygen because the coefficient in front of O2 is 2. So multiply the top, divide by 2. This is equal to 0.876 moles of CO2. So this tells us our limit is methane. This is our limit. This is our excess. So my correct answer is this one. This is the moles of CO2 that will be produced. So now we're going to find the moles of CO2, again using PV equals nRT, but now we're using the information provided by CO2. So my pressure is in ATM, so I don't have to convert again. I am looking for the volume this time of CO2. My moles of CO2 is 0.189 moles. Gas constant is still the same. Temperature is 125 degrees Celsius at 273 to convert to kelvins. So you're going to multiply all the right side together and then divide by 2.5. So VO2 is equal to 2.47 liters. So in this problem, since information is given on both of the reactants, we need to figure out which one was the limit. Since P, T, and V were given, we used the ideal gas law to solve for the number of moles. Once we solve for the number of moles, we could determine the moles of CO2 to figure out what the limit was. The smaller one is the limit, so methane became the limit. It produced 0.189 moles. Since volume, temperature, and pressure was given for CO2, we used the ideal gas law to find the volume of CO2. Pause the video, solve the problem on your own, and then check your answer. So here we have the density of gas measured at 1.5 atm, which is the pressure. The temperature is 27 degrees Celsius. And found to be density is 1.95 grams per liter. We are looking for the molar mass of the gas. So molar mass formula, there's two ways you could solve for this. You could plug into the formula if you memorize this. Density times gas constant times temperature divided by pressure. So if I plug this in, the density is 1.95 grams per liter. The density must be in liters because the gas constant is in liters. Gas constant is 0.08206 atm liters moles Kelvin. My temperature is 27 degrees Celsius plus 273 to convert into kelvins, divided by pressure, which is 1.50 atm. The other way you could solve for this is using molar mass and ideal gas law. So ideal gas law is PV equals nRT. So pressure here is still 1.50 atm. I know my volume because density is 1.95 grams per liter, which is 1 liter. So the volume here is 1 liter. I don't know the moles, so I'm going to look for the moles. And then R is 0.08206 atm liters moles Kelvin. My temperature is still 27 degrees plus 273. So I'm going to plug in and solve for the number of moles. Equals 0.06093 moles. Molar mass is defined as mass over moles. Remember, the mass was 1.95 grams divided by 0.06093 moles, which equals 32.0039 grams per mole without sig figs. So if I multiply the top, it becomes 32.0 grams per mole, same answer. So if we do sig figs, pressure has 3. There's a decimal significant digit in front of the 0, so that's 0 significant. The temperature has 3. Line up is precise in the ones place. Density also has 3, so my final answer has 3. The top one already has 3. This one, 1, 2, 3. I look 1 to the right, 32.0 grams per mole. So either method works, you'll still get the same answer. Dalton's partial pressure states that the total pressure exerted by the gases is the sum of all the individual pressure exerted by each gas. This individual pressure is known as partial pressure of the gas. There are 2 types of Dalton partial pressure that you will encounter in class. First one is a mixture of gases. If it's a mixture of gases, the total pressure is equal to all the pressure of each of the gases added. So if there are 3, it's going to be P1 plus P2 plus P3. If there is more, you need to continue to add. The second type is collected over water, underwater. Water is displaced. The equation becomes P total is equal to P gas plus P water. P water here will either be given to you or you will be solving for it because the pressure of water changes with temperature. So in this problem, a 22.4 liter glass bulb has a total pressure of 760 torrs and 0 degrees Celsius and contains 3 different gases, nitrogen, helium, and argon. They give you the partial pressure. What is the number of moles of helium in the tank? So in order to find the number of moles of helium in the tank, you need to calculate the pressure of helium. So we know this is a mixture of gas. So this is Dalton's partial pressure. So P total is going to equal to P of nitrogen plus P of helium plus P of argon. So P total is 760 torr. This is equal to N2, which is 250 torr, plus P helium, because we're looking for that, plus P argon, which is 130 torr, P helium, 380 torrs. If you line up the decimal, the least precise position is the tens place. So now if I look at what's given, I know the volume is going to be 22.4 liters because they're in the same container. P of the helium is 380 torrs. We know the temperature is 0 degrees. Since we have 1P, 1V, 1T, we know we have to use the ideal gas law. Here we cannot use 22.4 liters equals to 1 mole or molar volume because the total was at STP. However, the pressure of helium is not at standard pressure. So first thing I need to do is plug in for pressure, which is 380 torr. Since we're using ideal, I need to convert this into ATMs. There are 760 torr in 1 ATM. My volume is 22.4 liter because they're in the same container. I am looking for the moles of helium, the gas constant, ATM liters, moles Kelvin, and my temperature is 0 degrees Celsius or 273 kelvins. So I multiply everything on the left, divide by the numbers on the right, and you should get approximately 0.50 moles of helium. And so if we go back and do sig figs, this one has 3, this one has 2, and then this 0 is going to be significant because that's what's given, so that's 3. So I need 2 in my answer, and I have 2 in my answer. Next one, we have oxygen that is collected over water at 30 degrees in a 475 milliliter container. So I'm going to identify variables. So I know my temperature is 30 degrees Celsius. My volume is 475 milliliters. The pressure in there is 105 kilopascals. We're looking for the grams of oxygen. To find the grams of oxygen, I know I need to find the moles. Since I have 1V, 1T, 1P, I know this is going to be ideal gas law. PV equals nRT. But before we could even plug in, this is collected over water. So the first thing I need to do is I need to take out the water. So I need the dry gas. So that means P total is equal to P of water plus the P of gas. This pressure that was given is not the pressure of oxygen, but the total pressure. This is 105 kilopascals. Needs to be converted into millimeters of mercury. Kilopascal, this is 101.3 kilopascals, which is equal to 760 millimeters of mercury, which is equal to the pressure of water, which is 31.8 millimeters of mercury at 30 degrees Celsius, plus P gas, which here is O2. So PO2 is equal to 756 millimeters of mercury. So this is the pressure or the partial pressure of the dry gas or the O2. So I'm going to plug in 756 millimeters of mercury. It needs to be converted into ATMs because we're using ideal gas law. 760 millimeters of mercury, 1 ATM. The volume needs to be converted because it has to be in liters because of the gas constant. There's 1,000 milliliters in 1 liter. We're looking for the moles. That's NO2. Gas constant is 0.08206 ATM, liters, moles, Kelvin. Temperature is 30 degrees Celsius plus 273. So the number of moles of O2 equals to 0.19 moles. Since they want the grams of O2, we're going to do molar mass. So 0.019 moles O2. 1 mole of O2, 32 grams of O2. If you do the math, you should get 0.61 grams. And there should be 2 sig figs. If you line up the decimal here, there's 3 here because 105, even after I converted, I'm subtracting. So least precise is here. So it's going to be 3 digits or 2 digits after you convert it. Here there's 3, temperature 273, 30, least precise is here, so there's 2. So my final answer has 2. So pause the video, try this problem on your own, and then check your answer. So we have a helium collected over water at 25 degrees, so my temperature is 25 degrees Celsius. My pressure is 1.00 atm. What is the volume of the gas? When they give you a mass of 0.492 grams of helium. So we already know this is collected over water, so we have to do P total is equal to P water plus P gas. So that means the 1 atm that is provided is the total pressure and not the pressure of helium. So my total pressure is 1.00 atm. My water at 25 degrees Celsius is 23.8 millimeters of mercury. And convert that into atm, millimeters, so that's 760 millimeters of mercury to 1 atm. The reason I converted the water into ATM is because I know I'm going to use ideal gas law because I have one of each variable plus P gas. So my partial pressure of helium is 0.9686 ATMs. So now I use PV equals nRT. Since we already converted pressure into ATMs, I could just plug it in. If you didn't, you have to convert it back. So if you converted the 1 ATM into millimeters of mercury to solve and get the P gas in millimeters of mercury, since we are using ideal gas law, you need to reconvert it. To save time, I just converted the water into ATMs. My volume is what we're looking for. We need to find the moles since the mass of helium is given to us as 0.492 grams of helium. I do molar mass, which is 4.0 grams of helium to 1 mole of helium. Gas constant is still the same. And my temperature, I need to add 273. So if I plug all of the numbers on the right side, so multiply all the numbers on the right side, make sure you do the work in the parentheses first, divide by 0.9686, you should get a volume of 3.12 liters. So if I do go back and do sig figs, the temperature has 3 sig figs because 273 plus 25 least precise is the ones place. Pressure will have 3 after you convert it because you would have to do 760, which has 3. It's in the ones place, subtract, so you're going to end up with 3. Mass has 3, so my final answer has 3. 1, 2, 3 liters. So best way to solve for these is you look for keywords. If it's molar volume, just use 1 mole is equal to 22.4 liters. If you use gas laws, it just takes more work. If it's not at STP, make sure you identify the variables, figure out which gas law you need to use, and then figure out the stoichiometry if it needs to be done. If it's Dalton's partial pressure, look for mixture, keywords, mixture, collected, displaced, water. Those are your keywords, then you know it's a Dalton partial pressure. So majority of the time, you will either have to start with a P total equal to partial pressures of all the gases or water and gas, and then afterwards you would have to plug it into one of the gas laws.